Using Excel for Goodness of Fit Tests. This video uses the example titled Last Digits of Weights. The observed frequencies of last digits of weights are entered into cells A1 through A10 in the worksheet, and the expected frequencies are entered into cells B1 through B10. The Excel function chi-square.test and the Excel stat add-in can both be used to find the p-value for goodness of fit tests, but only Excel stat provides the test statistic and critical value. For this reason, Excel stat is recommended. In this video, we will begin with the procedure for Excel stat, followed by the procedure using Excel's chi-square test function. Excel stat can be used to calculate the test statistic and p-value for goodness of fit tests when frequencies and expected frequencies or expected proportions are known. Excel stat requires integers for frequencies and expected frequencies. If the expected frequencies are not all integers, as often happens, the expected data must be input as proportions. Begin by clicking the Excel stat tab in the ribbon. If Excel stat is not available, it must be installed. Instructions for installing Excel add-ins can be found at the website www.triolastats.com. Click the Parametric Tests button in the Excel stat menu and then select Multinomial Goodness of Fit Test from the drop-down menu. The Multinomial Goodness of Fit Test dialog box now appears in Excel. Click on any input item in the dialog box to select it, or press the Tab key to move to the next input item. In the Frequencies box, enter the range of cells containing the observed frequencies. In this example, we enter A1:A10. Cells can also be selected by clicking on the first cell in the data range and dragging the cursor down to the last cell in the data range. In the Expected Frequencies box, enter the range of cells containing the expected frequencies. In this example, we enter B1:B10. Expected proportions can also be used in this procedure by selecting Proportions under Data Format in the lower left of the dialog box. In the bottom right of the dialog box, enter the desired significance level. In this example, we use the default value of 5 for a 5% significance level. Check the chi-square test box. If the data range includes a data label, check the column labels box. If there is no data label, uncheck the box. In this example, we do not check this box. Select Sheet to display the results on a new worksheet. Click OK to display the results. The test statistic is labeled chi-square observed value. In this example, the test statistic equals 212.8. The p-value is also provided, and the p-value in this example is less than 0.0001. Because the p-value is less than 0.0001, we reject the null hypothesis. If using the critical value method of testing hypotheses, Excel stat provides the critical value of 16.919. The test statistic of 212.8 does fall in the critical region, so there is sufficient evidence to reject the null hypothesis. In this example, there is sufficient evidence to support the claim that the last digits of weights do not occur with the same relative frequency. Excel itself can also be used for goodness of fit tests. Begin by selecting an empty cell and then click the Insert Function button in the formula bar. The Insert Function dialog box now appears in Excel. Select the category Statistical. The selected item is highlighted in blue. In the Select a Function box, scroll down and click on CHISQ.test or chi-square test, and then click OK. The Function Arguments dialog box now appears. In the Actual Range box, enter the cell range for the observed frequencies. In this example, we enter cells A1 through A10. In the Expected Range box, enter the cell range for the expected frequencies. In this example, we enter B1 through B10. Click OK and the p-value will be displayed in the cell. The p-value in this example is displayed in scientific notation, and this p-value is so small that we can express it in different formats such as 0 plus or 0.0000, or p-value less than 0.0001. Note that Excel provides only the p-value. Excel does not provide the chi-square test statistic or critical value.